We've seen that the first derivative can give us some information about a function, like where a function is increasing or where a function is decreasing. We also know that the critical values of a function occur where the function's derivative is either 0 or undefined and the function itself is defined. The critical values might be relative maximum or relative minimum points. And we can use the first derivative test or the second derivative test to determine if those critical values really are relative maximum or minimum values. We also know that the second derivative will tell us about the concavity of the function. Where the second derivative is positive, the function is concave up, and where the second derivative is negative, the function is concave down. Where the second derivative is equal to 0 or undefined, we might have an inflection point. And we need to look at the sign of the second derivative in the intervals on either side of those values to determine if we really do have an inflection point. Now we're going to look at rational functions. The definition of a rational function looks pretty complex, but this is actually something fairly simple. A rational function is a function that can be described by the fraction p of x over q of x, where p of x and q of x are polynomials, and q of x is not the zero polynomial. What that means is that a rational function is a function that looks like a fraction. We know that the denominator of that fraction can't be a constant. The denominator has to have the variable x in it, and the numerator and denominator both have to be polynomials. Now the domain of this function is all the values of x that do not make the denominator 0. And we know that that also will help us determine where a function is continuous or where it's discontinuous. So for example, this rational function is discontinuous at x equals -1 and +1 because those two values of x will make the denominator 0. So the domain is actually split into these three pieces, from -∞ to -1, and also from -1 to 1, and from 1 to infinity. Now if we happen to have values of x which make the denominator of the function equal to 0, those values will represent a discontinuity in the graph. There are two kinds of discontinuities. One is called a removable discontinuity, which represents a hole in the graph, and the other is a non-removable discontinuity, which represents a vertical asymptote in the graph. Now the thing that's important to remember about vertical asymptotes is that your graph will never ever cross a vertical asymptote. So when your graph gets close to that vertical asymptote, it's going to just continue to get closer and closer, but it will never cross or touch the vertical asymptote. So let's look at this rational function and think for a little bit about what's going on in the graph of the rational function and how the function itself determines the shape of the graph. To determine what kind of discontinuities we have in this graph, we're going to factor the numerator and denominator, but we'll focus on the denominator to determine where our function is discontinuous. Remember, any value of x that makes the denominator equal to 0 represents a discontinuity in the graph. So in this case, we have 2 points where our graph is discontinuous, +1 and -1. Now the next question is, what kind of discontinuities are those? And to determine that, we're going to simplify the fraction by canceling out that common factor of x plus 1. And we'll look at this simplified form of the fraction. Now the factor that canceled in the numerator and denominator is important because it tells us where we have a hole in the graph. That's called a removable discontinuity because by canceling out that common factor, we were able to remove that factor from our original function. However, because x plus 1 was still a factor in the numerator and denominator, we still have to consider the fact that that value of -1 does represent a place in our function where our denominator was 0. But because it's a removable discontinuity, that represents a hole in the graph. Now, if you look at the graph, you'll see that there is a hole at -1, -1. And all we know at this point is that the x-coordinate of that hole is -1. To get the y-coordinate of that hole, we'll have to look at the simplified form of our function and substitute -1 in for x to get a corresponding y-coordinate for this hole. And as you can see, the y-coordinate is -1, which gives us our hole at -1, -1. Now we also have a vertical asymptote in this graph. That's the line x equals 1. That's a non-removable discontinuity. It's a factor that gives us a 0 in the denominator, but we were unable to simplify the fraction and get that factor to cancel out. So 1 is still making the denominator of the simplified fraction equal to 0, which means the vertical line x equals 1 is a vertical asymptote. As you can see, what happens with the graph is as we get closer to 1 from either the left or the right, our graph is getting really, really close, but it's never crossing it. Now let's look at one other thing that's going on in this graph, and that is that we have a horizontal asymptote as well. A horizontal asymptote is a horizontal line that our graph gets very, very close to as we get closer and closer to the edges of our graph. Since the horizontal asymptote is telling us what happens as our x-coordinates along our graph become very large or very small, what we're going to do is look at the limit of our function as x becomes very large, as x approaches positive infinity. As it turns out, that limit will be the same as the limit as x approaches negative infinity. So what we're really looking at here is the behavior of the graph as our graph either goes very far to the right or very far to the left. Now, in order to take this limit, we're going to do a little bit of an algebra trick. We're going to look for the highest degree term in either the top or the bottom. And what I notice is that x squared is the highest degree term I see. It happens to be in both the numerator and denominator. And what we're going to do is divide everything in the numerator and everything in the denominator by that highest degree term. Since we're dividing by the same thing in the numerator and denominator, we are not changing the fraction. It's just going to look like it's in a slightly different form. We'll divide every single term in the numerator and denominator by x squared. If you simplify all of those fractions, we get something that looks like this. Now here's what you need to think about. As x gets very, very large, the fractions that have the variables in the denominator get very, very small. For example, in the numerator of this fraction, we see a 4 over x. If you take 4 and you divide it by something that's huge, which is what's happening to x as x approaches infinity, 4 divided by something huge basically becomes so small that we are going to call it 0. So 4 over x is going to get very close to 0 when x goes to infinity. 3 over x squared also gets very close to 0. And 1 over x squared gets very close to 0. So this entire fraction becomes very close to 1 plus 0 plus 0 over 1 minus 0. All of the terms that have the x's in the denominator will approach 0 as x becomes very large. And 1 plus 0 divided by 1 minus 0 is 1. So what that's telling us is that as x becomes very, very large, y gets very close to 1, which is why our horizontal asymptote is the line y equals 1. Now, something to keep in mind about horizontal asymptotes is that we don't always have them when we have a rational function. We will always have horizontal asymptotes if the degree of the numerator is less than or equal to the degree of the denominator. If the degree of the numerator is larger than the degree of the denominator, then we will not have a horizontal asymptote. Now we'll look at a couple of other things on this graph. One is finding the Y-intercept. A Y-intercept happens when x is 0. So if we substitute 0 in for all of the x's, we'll get a -3 back out for y, which means the point 0, -3 is the Y-intercept. And we can also find an X-intercept. We need to find a point that has a y-coordinate of 0. So we'll set our fraction equal to 0. Now we have to look at the simplified form of the fraction to find the X-intercept. In other words, we have to remove that removable discontinuity. And now we can say that this fraction is equal to 0 when the numerator is equal to 0. So the numerator is equal to 0 when x is -3, which means that our X-intercept is the point -3, 0. So now let's look at this from the other direction. Instead of starting with a graph and trying to find these important points and these important asymptotes, let's start with a function and see if we can sketch the graph. So we'll start by looking for the intercepts. Remember, to find the y-intercept, we set x equal to 0. And when we do that in our function, we find that the y-intercept is -2. To find the x-intercept, we set the fraction equal to 0. And the fraction's only equal to 0 when the numerator is 0. But in this case, the numerator is the constant 8, which can never be 0, which means we don't have an x-intercept for this graph. So far, here's what our graph looks like. We have a y-intercept, but we don't have an x-intercept. Since we can't simplify this fraction, there are no removable discontinuities. In other words, there are no holes in this graph. However, there are some values that make the denominator 0, some non-removable discontinuities, which represent vertical asymptotes. To find those values, we'll set the denominator equal to 0 and factor, and we find that there are two values for x which make the denominator equal to 0. That means we have two vertical asymptotes on our graph. The vertical lines x equals -2 and the vertical line x equals +2. For the horizontal asymptote, we're going to think about the limit as x approaches infinity of our fraction. Well, the limit as x approaches infinity is 0, because if we let x become very, very large in this fraction, our fraction will get close to 8 divided by a huge number, which is equal to 0. So our horizontal asymptote is the line y equals 0, which is the x-axis. So this is what our graph looks like now. We still have our point at 0, -2. That was our y-intercept. But now we have these vertical asymptotes and horizontal asymptote that are dividing our graph up into some pieces. Now, to figure out what those pieces look like, we can look at the first derivative to determine where the function's increasing and decreasing, and if we have any relative maximum or minimums. So we can take a derivative by using our quotient rule and by simplifying. And then we can look for critical values. Critical values occur where our first derivative is either equal to 0 or undefined. 0 will make our numerator 0. So 0 is a value that makes our first derivative equal to 0. And 2 and negative 2 make our denominator 0. And if our denominator is equal to 0, our first derivative is undefined, so we have to consider those as critical values as well. Now, if we make a sign chart for those values, the 0, the 2, and the negative 2 will divide our domain into 4 intervals. We know that we have vertical asymptotes at negative 2 and positive 2, so we will definitely not have a relative maximum or minimum at those 2 points, but we still don't know what's happening at 0. So if we look at these intervals and we find a test value in each of the intervals, and we substitute those test values into our first derivative to find the sign of the first derivative in the test values, we'll find out that in the first interval, our first derivative is positive. From negative 2 to 0, our first derivative is also positive. From 0 to 2, our first derivative is negative. And from 2 to infinity, our first derivative is also negative. So this is absolutely no different than we did with polynomial functions. We're just substituting test values into our first derivative to look for the sign of the first derivative, in other words, the slope of the tangent lines along the curve in those intervals. So we know our function's increasing and still increasing, and then decreasing and decreasing in our 4 intervals. Now, how do we tie that together with our graph? Well, we certainly know that this point where x is 0 has to be a maximum. So we can find the y-coordinate that goes along with that x-coordinate to give us another point on the graph. And to find a y-coordinate, remember we always substitute our value back in our original function. So we have a relative maximum at 0, negative 2. Well, we already have that point on the graph. That was our Y-intercept, but that point also is a relative maximum. So if we think about where our function's increasing and where our function's decreasing, we know it's increasing from negative infinity to negative 2, and also from negative 2 to 0. And then it's decreasing from 0 to 2, and from 2 to infinity. So we'll take a second derivative to figure out where our function's concave up and concave down, and to find inflection points. Since we have a rational function, we can use our quotient rule and simplify to get our second derivative. Now we need to find the values for x that will either make our second derivative equal to 0 or undefined. In this case, our second derivative is never equal to 0 because the variable factor in the numerator, the 3x squared plus 4, is always positive. But the denominator is equal to 0 at 2 and negative 2. So those are the values we need to look at for our sign chart for our second derivative. Negative 2 and positive 2 break our number line into 3 intervals. But we know that there are vertical asymptotes where x is negative 2 and where x is positive 2. So we won't have inflection points there. However, we can still look for the concavity in each of those intervals by looking at some test values in each interval. Now remember, we're looking for the sign of the second derivative. So we'll substitute the test values into our second derivative to see whether that value is giving us a positive result or a negative result. When x is negative 3, our second derivative is positive. When x is 0, our second derivative is negative. And when x is 3, our second derivative is positive. So we know that our function is concave up from negative infinity to negative 2. Then it's concave down from negative 2 to 2. Then it's concave up from 2 to infinity. This is exactly like we did with polynomial functions. But the difference here is we have these vertical asymptotes breaking our graph up into 3 pieces. So now that we know something about the concavity on these intervals, let's put this together with our graph. Knowing about the concavity on these intervals just allows us to refine what our function looks like, to get the curves of our graph correct. Now the other thing we can always do is just pick some values out for x and substitute them into our original function to get some y coordinates back out to get some points to graph. And once we do that and we put that together with the information about concavity, we'll end up with a graph that looks like this. Now it may seem like we're going through a lot more steps to graph rational functions, but we're really not. Just like with polynomial functions, we're still using a first derivative and a second derivative to determine information about the graph. The derivatives themselves can be a little bit messier because we're dealing with fractions. So we're dealing with things like the quotient rule, which we know can be a little bit messier. And we're dealing with some simplification of these algebraic expressions, which also can take a little bit more time. So let's look at one more graph, and this one has something interesting going on. The thing that's the same as the last graph that we looked at is that we still have a vertical asymptote. That's the vertical line x equals 1, because when x is 1, the denominator of our fraction is equal to 0. But we don't have a horizontal asymptote. And that's because the degree of the numerator is larger than the degree of the denominator. The numerator's highest exponent is 2. That's from the x squared. The denominator's highest exponent is 1. That's from the x, which is really x to the first power. However, we do have this asymptote, which is called an oblique or a slant asymptote. Now, a slant asymptote will happen if the degree of the numerator is larger than the degree of the denominator. And there is a way to find it, but we're going to have to do a little bit of algebra to get there. So let's see how we find that slant asymptote. So the first thing we're going to have to do is fall back on some algebra, which is to actually do a division of x squared minus 4 divided by x minus 1. So this is a long division with polynomials. You may remember that to do long division with polynomials, we look at the first term on the inside and outside of our division problem, the first term in our dividend and our divisor. And we can say, well, let's see, x squared divided by x would be x. And then we multiply x times x minus 1. We subtract. And then we say, well, let's see, x times what gives us x? Well, that would be 1. So 1 times x minus 1 is x minus 1. And then we subtract and we get negative 3, which is a remainder. But it also is the numerator of the fractional part of our division, the fractional part of our quotient. So x squared minus 4 divided by x minus 1 is the same thing as x plus 1 plus this fraction, negative 3 over x minus 1. Now remember that in order to find a horizontal asymptote, we took the limit as x approaches infinity. We wanted to know what happens way on the edges of our graph. We still want to know the same thing with an oblique asymptote. So we'll take the limit as x approaches infinity of this version of our function that we got by doing the division. Now as x gets very large, as x approaches infinity, the fraction gets very close to 0, because negative 3 divided by something really large becomes something very, very small. So when we take our limit as x approaches infinity, the fraction in essence becomes so close to 0 that this expression becomes really close to x plus 1. So we can say that y is getting really close to x plus 1, which means the equation of our oblique asymptote is y equals x plus 1. So if you look back at what that slant asymptote looks like in our picture, you can see that it is a line that has a slope of 1 and a y-intercept of 1. And if we can graph that slant asymptote and then go ahead and look at our first derivative and our second derivative to determine where our function's increasing and decreasing and where our concavity is, we can still put all those pieces together to make our graph. So remember, this may look complicated because there are a few more steps involved, but most of what we're doing to graph rational functions is exactly what we've been doing to graph polynomial functions. We just have a little more information to add to the big picture that we have when we're graphing our function.